Has everyone been following the recently concluded CES 2026? In this year's battery exhibition area, a very strange, yet exciting phenomenon occurred. In the past, when we talked about battery technology, the boundaries were clear. Solid-state batteries were the kings of energy density, responsible for long-range travel. Supercapacitors were the kings of charge-discharge speed, responsible for going fast. But this year, this boundary seems to have been blurred. Look at what ProLogium technology exhibited. The ultrafluidic all-inorganic solid-state battery. It claims to be able to charge to 80% in just 5 minutes. And there's Verge's electric motorcycle, which even claimed a battery life of 100,000 cycles. Wait a minute, fully charged in 5 minutes? A lifespan of 100,000 cycles? This sounds nothing like the lithium batteries we know. These specs actually sound more like supercapacitors. So, a certain voice started appearing online. Have solid-state batteries evolved to the point where they can completely replace supercapacitors? Do we still need to develop capacitor technology? In today's video, we aren't just going to look at the hype. From the perspective of an electronics professional, I'll take you through the technical truth behind this. As solid-state batteries become more like supercapacitors, will these two technologies compete with each other, or will they join forces? First, we need to correct a concept. Although the solid-state battery data from CES is very impressive, it's fast like a capacitor, but in their physical essence, they are still completely different from supercapacitors. Simply put, no matter what black magic technology solid-state batteries use, they still operate based on chemical reactions. Lithium ions must migrate from the positive electrode to the negative electrode. This process is like moving houses. Although solid electrolytes have turned dirt roads into highways, allowing ions to travel at high speeds. But in the end, there must still be a chemical process of intercalation and deintercalation. As for supercapacitors, they rely on pure physical adsorption. Charges are directly attached to the electrode surface, just like Velcro. Sticking them on is charging, tearing them off is discharging. It doesn't require a chemical change. This determines the core difference between the two. Let's compare the first round, the real speed of charging and discharging. When solid-state batteries talk about 5-minute fast charging, they mean filling up a massive amount of energy takes 5 minutes. But the fast in supercapacitors means they can release all their energy in a few milliseconds or even less. This makes a big difference in application. If you want a car to drive 500 kilometers, you need solid-state batteries. But if you are firing an electromagnetic gun or dealing with the instant startup of a laser cutter, the chemical reaction speed of solid-state batteries is still too slow. In those moments, only a supercapacitor can keep up. Round 2. The lifespan trap. The 100,000 battery cycles mentioned at CES are indeed a massive breakthrough in materials science. Usually, this is achieved under specific experimental conditions. But the 500,000 or even 1 million cycles of a supercapacitor are part of its basic physical properties. Because there is no chemical reaction, the electrode material won't age due to repeated expansion and contraction like a battery. Therefore, in scenarios with extremely frequent charging and discharging, such as factory automation equipment, the supercapacitor is still king. Next, let's look at the third round, the energy density chasm. This is the eternal pain of supercapacitors. Currently, top-tier solid-state batteries are pushing towards 400 watt-hours per kilogram or even higher. But supercapacitors are still struggling around 10 watt-hours per kilogram. To put it bluntly, if you used supercapacitors for a phone battery, it would charge in 1 second. Yes, but you might run out of power after 5 minutes of use. So, at this point, the conclusion is clear. The progress of solid-state batteries is not meant to kill off supercapacitors. Instead, It makes cooperation between the two more likely. The most obvious example is currently the hottest AI servers, like NVIDIA's GB200 system. Why do their power modules still need capacitors? Because when a GPU is computing, the fluctuations in instantaneous power consumption are very intense. It happens faster than even the best solid-state batteries can respond to. That's when you need supercapacitors or high-quality capacitors to perform filtering and peak shaving in between. This protects the subsequent circuits and prevents grid collapse. It's the same for electric vehicles. The golden combination of the future will likely be a solid-state battery responsible for long range, paired with a set of supercapacitors to take the bullets. Instant high currents like starting, acceleration, and regenerative braking, which damages batteries, will be handled by the supercapacitors. Stable cruising power will be handled by the solid-state battery. This way, the car can travel far, and the battery life can truly last as long as the car itself. In summary, CES 2026 tells us that solid-state batteries are working hard to make up for their shortcomings in power, turning themselves into all-around players. But supercapacitors remain that irreplaceable less-full forces unit, specifically solving the most extreme and fastest energy demands. What do you think about the future of these two technologies? If you are buying an electric vehicle, would you want it equipped with this solid-state battery that claims to fully charge in 5 minutes? Or would you trust a more traditional lithium battery paired with a supercapacitor hybrid? Welcome to leave a comment below and tell me what you think. If this is your first time visiting this channel, don't forget to subscribe and turn on the notification bell. We specialize in sharing this kind of hardcore tech knowledge. See you in the next video. Bye-bye.